I'd like to review a few things about Lesson 7. Lesson 7 is not an easy lesson at all because now you really have to apply the techniques you learned in the previous lessons in a more conceptual context. That means you have to translate your knowledge about how to compute derivatives and so on into a context where you have to apply what you know, and that's really not easy. So after my poll on Piazza and also after looking at the returns of the first quiz attempt uh, in Angel, I've decided to focus on the following three things. So first, identifying a graph from the properties of its derivatives. Um, that's again going over uh, how a graph or what the derivatives can tell us about the form of a graph. So there's this we can go over a few problems from the book, and they occur in a similar form on the quiz, as if you've taken the first attempt, you may have already noticed. Then finding max and min, so extrema, global, and local. That's really one of the core applications of calculus, that it can actually help us find uh, maxima and minima of functions, which of course is often of very great importance in business applications and so on. And then the third um, problem type I want to go over are text problems. The problem with the text problems is really often that the mathematics behind them is not too hard. It's more that you have to get from the text to the right mathematics to do, and that's the hard thing. Unfortunately, it's not that easy to train this. There's no kind of fixed algorithm like, say, the chain rule. You know what to do once you see the function. But you really have to pay close attention to the details of the text and try to extract exactly the data that you need and set up a mathematical problem that you then can solve. I've decided to make this lesson a little bit more problem oriented. So I've picked according to problem from the book, and we'll go over it and along the way try to explain the steps of the solution a little bit more and also the concepts that are involved in finding the solution. So this is section uh, 4.2, I believe, um, number 26. And if you've taken the quiz, you see that there's a similar problem like this on the quiz, even a little bit simpler because you get the graph as or possible solutions as a multiple choice question. Here, what this problem asks you is to uh, identify or sketch a possible graph of the function y, right, based on the information that's given to you about the first derivative and the second derivative, so y prime and y double prime. So if you recall the derivative, the first derivative always gives us information about whether the original function y is increasing or decreasing on an interval. Right? And this information is given to us here. Right? So here we have positive first derivative, negative first derivative. So we immediately can infer from this on this interval the function must be increasing. On this interval here, right, it must be increasing too, and here it must be decreasing. And in these points, which we now know are the critical points, we have horizontal tangents. So at this very point, these very points, the function is neither increasing nor decreasing for this very moment. Now let's look at the second derivative. The second derivative, if you recall, tells us whether the function is concave up or concave down. Right? So here we have negative second derivative, so we know it's concave down. And here we have positive second derivative, meaning it's concave up, and here again it's concave down. And this information already tells us a lot about the form of the function, so we can actually now already go ahead and sketch a graph. Right? So let me draw the x-axis here with the intervals that are given to us from the information up here, right up here. And now we know in this first interval the function must be increasing, right? It must be increasing and concave down. Well, let's draw this. Right? It's something like this. It's increasing concave down. Then in the second interval, right, up to here, so this interval here, we know it must be increasing, positive first derivative, and concave up. Right? Okay, something like this. And then here we have, while the function keeps increasing in this interval, it turns from concave up to concave down, right? Concave up to concave down. That's called an inflection point. Right? So it keeps increasing, but it's now concave down. And then finally, right, the function turns from increasing to decreasing. So while it stays concave down, right, so we actually go down now. So this is a possible graph of the function. And you see, it's actually, I hope, not that hard once you kind of sketched out all of the properties that you need. I mean, drawing increasive concave down is straightforward, and concave up, and so on, right? And you all also notice here, right, that we have the critical points are reflected by the fact that we have horizontal tangents there. And the inflection points are also reflected in here. We have an inflection point over here and another inflection point over here where the concavity changes. It's also reflected here in the zeros of the second derivative. Okay, so this was an example of how we can use just information we are given through the properties of the derivatives to actually sketch a graph of the function. What we cannot do here is, however, to actually say how stretched along the y-axis, or where actually along the y-axis this function is, right? Let's do another one of these examples here. So this is same section 4.2, number 27 now. And now we're given the following data. So we know that y prime, so the first derivative, is less than 0 everywhere, right, on the whole interval. That's nice. So we know immediately it's always decreasing. So the function is always decreasing, right? So we can turn our attention right away to the second derivative, right? And here we know, right, it's concave up. Let me write this here: concave up, concave down, up, and down. So it's a roller coaster ride downward, right? So it's like a downhill with pauses or breaks in it. You can imagine. Okay, so let's try to sketch it. Let's take the x-axis here. Again, it doesn't tell us, the derivatives cannot tell us about where along the y-axis the function is or how far it is actually stretched out along the y-axis. That's nothing that the derivatives give us information about. However, we can now sketch the properties or do an approximate sketch taking into account the properties we do have, right? Decreasing and concavity. Right, so here are the intervals. And we start decreasing, so it's always decreasing, so let's start up here. And we start decreasing concave up, so something like this. Right? And then we change to decreasing concave down, something like this. Right? And then we change to decreasing concave up. You can almost think of it as some kind of a building block set, right? So if you had one of those, or if your children have one of those wooden railway sets, right, or just a railway set, they come with these fixed rail sets, right, and they have curves, and you put them together and you can build something similar here, right? So that's what it reminds me of, at least. So you have concave up, concave down, decreasing, concave up, decreasing, and then again concave down, decreasing. Something like this. I should stress here, it's important that we don't have zeros in the derivative. So here, even though it looked like we might have a horizontal derivative, it should not be strictly horizontal, right? Because we have no critical points, right? So here too, so there's no break in the decreasing, right? It's always strictly decreasing. Okay, so here's an approximate sketch. So if you want to draw it a little bit more pronounced and compressed, so we would have something like decreasing concave up, decreasing concave down, decreasing concave up, decreasing concave down. So here you see even more pronounced the way this railway kind of construction set, right? You have concave up, concave down, decreasing, increasing. So in the quiz, when you see a similar problem, right, a problem of this type, what you do is, I always first translate the properties of the derivative into properties decreasing, concave up, concave down. So increasing, decreasing, concave up, concave down. Right? And with the accordant intervals, right? So that you're given. Right? So in the quiz, you will be asked, for instance, the first derivative is increasing for all x greater than 5 or something, right? Then you know, well, you know that it will be increasing. So so it's greater than 0 for all x greater than 5. That means it's increasing to the right of 5, right? So really write down the list of properties you can infer from the given data for the graph, right? And then try to sketch the graph out yourself before choosing from the given alternatives, right? Try to kind of already get an impression yourself what the graph should look like, and then look at the 5 different choices. And you will then hopefully see right away which one you have to choose. Next we get to finding minima and maxima of functions. And there's a rather tricky problem on the quiz, and it's related to similar problems in the textbook. And it has to do with, you are given the graph of the derivative, not the graph of the function. That's very important. You're given the graph of the derivative, right? F prime. And you are asked, so first to find the critical points of the function f itself. And then further determine at which critical points does f have local maxima, local minima, or neither. So let me take this opportunity to go over the basic concepts of local minimum, local maximum, and global minimum maximum again. So you can think of like maximum or minimum. Let's take an example, the tallest building, right? So if we take the word global literally here, right? So it would mean the tallest building in the world, right? So it is really, there would be no other building that's taller than that specific building anywhere in the world, right? So that would be a global maximum for a function, right? So in the context of functions, a global maximum would be assumed at a point such that the value of the function at this point, right, is larger, or at least as large as any other function value at any other x. So equally we have, or correspondingly we have minimum, right? So let's say the deepest trench in the ocean, the deepest point on Earth, right, on the surface of the Earth, is given somewhere in a trench in the Pacific, I believe, right? And this would be a global minimum. Nowhere on Earth you can reach a deeper point, right? And you could see here in this function, right, you have indeed a global minimum, right? At this point here, right, there's the function f reaches a value that is lower, or at least as low as all other function values, right? No other function, at no other x, right, the function reaches a lower value. You can always think of it like you take a horizontal line that's given by this function value here. Right? Take this horizontal line, and if it's a global minimum, this horizontal line will not be crossed downwards. So at no point does the graph of the function, right, cross this line downwards. Okay, so that's why this point here is a global minimum. And as you can see now, this function here has no global maximum, because for any potential maximum, right, so over here, for instance, this line, horizontal line, is no, right, it will be crossed upwards, right? And so will any other line. So if you imagine this function continuing over here and over here, right, it will always be crossed upwards. So there is no global maximum. There is no highest point on this graph, so to say. Now local maxima and minima are kind of maxima relative. So now think of tallest building in a specific city, right? That doesn't mean that it's the tallest building of the world, but relative to its neighborhood, it's very tall and it's the tallest, right? The same idea gives us the idea of a local max and a local min of a function, right? So let's look, for instance, at this point here. This is a local max because there is some neighborhood, right? So think of it, there is some town around this, right? So there's some interval, mathematically speaking, such that at this point, right, this point here, right? So if you now think of it like we draw a little bit circle around this, right, and focus exclusively on this circle. Within this circle, there is no higher point on the function than this black dot here, right? So that's why this is a local max. Likewise, if we draw a little circle around here, right, corresponding to an interval down here, there is no lower point on this function, right, than this black dot here in this red circle. So that's why it's a local minimum. But the important thing is you can kind of find the interval, or the kind of the little world or town in which you're the tallest or the smallest yourself, right? And because it does not need to hold that for every interval you draw around this point, you have to be the greatest or the tallest or the smallest, right? So if I draw an interval around this point here, right? So down here, if I drew this interval, right, say like this, then we would see within this interval, right? So now, right, coming up to here and up to here, we see within this interval, right, within this greater local world, so to say, this is no longer the largest value. So it's, but for being a local max, it suffices that there is some little world around you, right, in which you're the tallest in case of a local max, or the smallest in case of a local min. Now, how does the derivative come into play here? Well, you already see it in the graph, right? Because if you look at where are the local max, the local min, and the global and local min here are assumed, well, they're all at points where the tangents to the graph are horizontal. That means the first derivative vanishes there. And if you think about it, it's really not a big surprise that it does so. Because let's see the case of this local maximum here. What does it mean that you're a local maximum? Again, well, within some neighborhood, right, you have to be the tallest or highest point on the graph. But that means that to the left and right of you, the points are smaller, right? The values are smaller. They're below you. But that means that leading up now from the left, right, coming from the left, the graph has to be increasing, right, because they're leading up to the maximum. And once they reach the local max, the graph has to be decreasing because the values have to become smaller. That means at this point, right, the graph changes from increasing to decreasing, and hence has a brief moment where it has a horizontal tangent. Right? That means it is a critical value. That's why derivatives are so helpful, right, in determining maxima and minima of graphs, because they capture the increasing decreasing behavior. In particular, they tell us when something switches from increasing to decreasing and vice versa. So let's get back now to our original problem, number 23 in section 4.1. So now we are asked to determine the critical points of the function from the graph of the derivative, right, and then see whether the function has local maxima, local minima, or neither. Okay. So let's zoom in and into the graph and see what we can do about this. Okay. First, we're asked to determine the critical points of the function. But remember, this is the graph not of the original function, but the graph of the first derivative. Critical points correspond to the x values where the first derivative vanishes. There's also the case where the first derivative is undefined in x. That would also be a critical point, but this does not apply here because it's this graph we see, it's defined everywhere. Okay, so to find the critical points, we have to find the zeros of the first derivative. But that's easy because we just have to look at the y-intercepts. The x-intercepts. And we have 3 of them. So we have 3 critical points. So here we have critical points. Now the question is, which of these critical points correspond to a local minimum, a local maximum, or neither? So let's go and analyze the graph of f prime in this respect. So here we have the first critical point. What happens to the graph of f prime there? Well, we see it changes from positive up here to negative down here. What this means is for the original function that at this point here, f changes from decreasing, from increasing, because increasing to decreasing, right? Because f prime changes from positive to negative. So what does it mean for the graph of f? Well, it changes from increasing to decreasing. It looks something like this, right? So here and x, right, at this point, we actually must have a local max. Right, because f prime changes from positive to negative, hence f changes from increasing to decreasing, right? And that's precisely that phenomenon we saw on one of the previous slides that corresponds to a local max. Now let's look at the second critical point here. What happens there is that f changes from, so f prime changes from positive, from negative to positive. That in turn means again now that f changes from decreasing to increasing. Right? And for the graph, that means that it looks something like that. It comes down decreasing and then changes it to increasing at this point. But this corresponds to a local min. So this critical point here corresponds to a local minimum of f. Now let's look at the last critical point. That's an interesting one because what's happening there, right? F is coming in positive and it stays positive. It just touches the x-axis. It never actually becomes negative. That means in terms of f, right, f is increasing, takes a break, and stays increasing. So in terms of the graph, it would look something like this. It's increasing, takes a break where it has a horizontal tangent, and then increases again. So here we'd have the horizontal tangent, right, which corresponds to the 0 of the derivative, right, here. But it does not change sign from increasing to decreasing, it just stays increasing. Right, so derivative does not change sign, so f stays increasing. It just takes a break, so to say. Right, so this is neither. This points to an important fact, and it's a frequent source of errors and misunderstandings. Namely, a critical point can be a local min or max, but it does not have to. So when you find that the derivative of a function vanishes somewhere, it is possible that there is a local min-max there, but it does not have to be one. And the example of the third critical point on the previous problem actually is an example for that, right? So we had a critical point, but it did not correspond to a local min or max. So let me illustrate this with another even more simple example. Just take the function f of x equals x to the third. So that looks something like this. And you see, if you compute the derivative, right, f prime of x using the power rule is 3x squared, and that is 0, right? So f prime, now we see f prime of 0. If we plug in 0 here for x, we get that this is 0. So 0 is a critical point. 0 is a critical point, but it is clearly not a local min nor a local max. And if you do this sign test, you see actually at 0 the derivative does not change sign. It does not change sign here because it always stays positive. It just takes a break, right? Because it touches, the derivative touches the x-axis. So how do we then determine, if we have a critical point, whether it corresponds to a local min or max? Well, one way, as we have done in the previous example with the graph of the function, would just be to see, does the first derivative actually change sign at this point, at the critical point? If it does, then we have a local min or a local max, depending on whether it changes from decreasing to increasing or from increasing to decreasing. Okay. We could also say, well, the other idea would be to see, okay, if the function looks like this, and we do have a local min, right, for instance here, the concavity actually stays at concave up in this point, right? Whereas here, in this example, the concavity changes from concave down to concave up. And that's the idea of the second derivative test, to see that the concavity is actually strictly concave up or strictly concave down at this critical point. So let's go over the second derivative test with an example. This is our function, f of x equals 1/2 x to the fourth plus 4/3 x to the third. We're not plotting the graph now, because one of the nice things is you can apply all these tests without knowing what the function looks like. In fact, often these kind of computations are what tell you actually what a graph looks like. So let's try to do this step by step for this function. So the first thing we would have to do is to compute the critical points. Well, let's compute the first derivative. F prime of x is, by using the power rule now, it would be 4 times 1/2 x to the third plus 3 times 4/3 times x to the x squared, right, and that's the same as 2x to the third plus 4x squared. And this we can write a little bit easier as, we can write this as 2x to x squared times x plus 2. Now we have to ask, when is this 0? And by writing it in this way here, it makes our life a lot easier, because when is this expression 0? Well, exactly when one of the two factors here is 0. Either 2x squared is 0 or x plus 2 is 0. So we immediately see that the critical points are at x equals 0, right? When this is 0, then this factor here becomes 0, or x is equal to minus 2, right? Because in this case, this parenthesis expression here becomes 0. Now, which of these critical points corresponds to a local min, max, or nothing? Well, we could either do the sign test for the first derivative and analyzing when this changes sign. This is possible, but I find that often a little bit tedious because you have to look at, okay, we have minus times minus when this is less than minus 2 or whatever, right? So let's compute the second derivative and do the second derivative test, right? So let's put the second derivative, f double prime of x, right? So this would be, it's easier to use this form now to compute the second derivative of it. So let's do this, and we get 6x squared plus 8x. Okay, and we could, if you want, you can write this again in a form like, what do we have? 2 times 3, 2x times 3x plus 4. So what you do now in the second derivative test is, after you computed the second derivative here, you plug in your critical values into the second derivative and see what it gives you. And the sign of the second derivative, right, at these critical values will tell you whether it's concave up, concave down, or neither. Okay, so let's do this. Let's start with this one here. So we would have f double prime of 2. So here we would have 6 times minus 2 squared, so it would be 4, plus 8 times minus 2. So that would be 24 minus 16, that would be 8. So this is a value greater than 0. So that means at our critical point minus 2, the function is concave up. So that means at this value it corresponds, at this x, it corresponds to a form like this, right? Whereas here we have x equals minus 2. And that in turn means it's a local min. So let's write this again a little bit more cleanly. So we have our critical points, x equals 0, x equals minus 2. Here's our second derivative, and we have just computed that f double prime of minus 2 is equal to 8, which is greater than 0. So that in turn implies that the function is concave up there, and that in turn implies that we have a local min. Now let's do this for the other critical value, 0. Let's plug this in, f double prime of 0. Now we see that's easy to compute because it's just 0 plus 0, which is 0. So that means there the function is neither concave up nor concave down. So the test in this case is inconclusive. That's also important to point out, that if it's neither greater than 0 nor less than 0, it does not necessarily tell us that there is no local min or local max. It just means we have to use a different method. So for instance, the change of sign test for the first derivative. Okay. So in this case here, we can actually see then, if we do that, the function, the first derivative, does not change sign at 0, right? And we get that we have actually neither. So neither local min, local maps. So I've drawn the function here on my computer, and you see our computation seem to be correct. Right? We have a local minimum here at -2, right? And it turns out that this is actually in this case a global minimum. Right? And here we see, while we have a critical point, horizontal tangent, the function just takes a break. Right? It changes concavity, hence it just takes a break from being increasing. Right? So no local min nor local max there. So let's go over the steps again that we took. Well, the first was we compute f prime, find the zeros. This will give me the critical points. Then third was compute f double prime and check whether compute f double prime of the critical points and check whether this is greater than 0 or less than 0. If either of those is the case, you know immediately it's either a local minimum, if this is greater than 0, right, because then it's concave up, or it's a local maximum if it's less than 0, because then it's concave down. If it's equal to 0, the test is really inconclusive. It may, usually it does point to something like this here, where the function takes a break, but it does not have to. In the third part of this lecture, I want to do some text problems. And as I already said, that the problem with these text problems is there's no kind of algorithm you can usually train or just learn. Just like, for instance, in the second derivative test, there's a number of kind of very well-defined steps you have to take for any problem that of this type. For these kind of text problems, the mathematics is usually not that hard. The problem is to get the right model and to get the right setup so that you can just solve it mathematically. So I want to go over 3 examples or 3 problems, and hopefully this gives you an idea of how you do it, how to do this the mathematical setup. Okay. So this here is problem 4.3, section 4.3, number 36. If you have 100 feet of fencing and want to enclose a rectangular area up against the long, straight wall, what is the largest area you can enclose? Okay. So the first thing you should always do is, I always do a drawing or something that helps me visualize and then conceptualize what I'm actually asked to do here. Right? So here in this case, we have a long straight wall. Let's assume this is the wall. And then we have fencing, and we want to enclose a rectangular area up against that wall. So let's assume we have fencing. So what we want to do is we want to take our fence and enclose a rectangular area like this up against that wall. So our fence has like 3 sides, right? 2 of which, since it has to be rectangular, and that's another important information we're given, so it has to be a rectangular area. That means we have 2 sides here of the same length, and 1 side, right, that is parallel to the wall. The wall is already given, so we don't need to do any fencing there. So we have 3 sides, 2 of which are equal. Okay, so let's denote this here by x, denote this side by y, and since this is equal to the other side here, we can put x in here too. So this is the first step in doing the mathematical modeling. We are assigning variables to the kind of important sizes or dimensions that are given to us from the problem. Okay. So what else, or what other information does the problem give to us? So that's really the important step, the first step, and it's actually the most important step in that in solving these kinds of problems, is to go and try to extract and squeeze every bit of information out of these problems that you have and put them into a mathematical formula. So what is given to us? We have 100 feet of fencing, so we also know how much fencing we have, total fencing we have, and it says 100 feet. So what does this mean mathematically? It means that the length of the red line here, right, is 100. In mathematical terms, this means that x plus y plus x is equal to 100. So we can also write this, of course, as 2x plus y is equal to 100. So this is the complete mathematical information that is given to us. Well, not quite yet, because we haven't defined our objective yet, but this is kind of the basic information given to us through the problem. Now let's look what the problem actually wants us to do. Well, it wants us to compute the largest area we can enclose this way. Okay, now we have to find what is called the objective function. It's the function that we actually have to optimize in this case. Right? So what do we want to optimize? Well, we want to optimize the area. We want to find the largest area. Right? So in this case, you have to find a mathematical expression for this area. But that's easy using geometry, right? What is the area of this? Right? This is what we want to maximize. The area, let's call it A, is just length x times y here. Length times width, because it's a rectangle. Right? Area A. And this we want to maximize subject to this condition, that 2x plus y is equal to 100. Okay. Now, usually these conditions then, in these text problems, give you a way to turn this from a 2-variable problem into a 1-variable problem. And that's exactly what happens here. Because we can write from this, we can write y as 100 minus 2x. Right? So we can rewrite our area equation, right, as x times 100 minus 2x, which is the same as minus 2x squared, plus 100x. Okay. So now what do we do with this function? Okay, right? Well, we want to find the maximum, because we need the largest area. For which x does this rectangle have the largest area? So we have to compute a global maximum. But that's not too hard. We know how to do this because we have a function. We just take the derivative and then take the second derivative test. So let's do it. So a prime is equal to minus 4x plus 100. So the critical point would be x equals 25. Okay. So now we have to test whether this is actually a local min or local maximum. Sorry. So let's take the second derivative. But that would be just minus 4. So we have a double prime of 25, which is our critical point, is equal to minus 4, which is less than 0. So we have a local max. So now the only question is this local max actually a global max? But now we look at the form of this function. This is a parabola, right? And it's a parabola that's open downwards, so it's concave down. It's concave down everywhere, in fact, as we see from the second derivative, right? And therefore, it must actually be global max, because it's the tipping point of a parabola, right? It's the top of a parabola. So it is actually a global max. So at x equals 25, we obtain the largest area. So that means, what is y then? Y is 100 minus 2x. So 100 minus 2 times 25, which is 50. And now we can compute the area from this, right? So it would be, A would be here 25 times 50 square feet. So that would be 1,250 square feet. And that's the answer. Let's do another text problem, this time from the business application. So here's the problem. The demand equation for a quantity Q of a product at price P in dollars is P equals minus 5Q plus 4,000. Companies producing the product report that the cost C in dollars to produce a quantity Q is C equals 6Q plus $5. Now the first thing we need to do, or asked to do, is express the company's profit in dollars as a function of Q. Okay, so for part A, we know that profit pi is equal to revenue minus cost. Right. Revenue, in turn, is price times quantity. So it would be P times Q minus C. Now we can plug in the whole thing that we know. Right? It's P times Q, so it would be, we have the price equation given up here, or demand equation, sorry. So we have P expressed in terms of Q, so we can just simply plug this in. So we have 5Q plus 4,000 times Q minus C, but C is given to us as 6Q plus 5, so we can do minus 6Q plus 5. Okay, now let's just simplify this. So this would be minus 5Q squared. Then we have 4,000Q minus 6Q, that would be plus 3,999 94Q, and then we have a minus 5 here. So in this problem, the first step is not so much using geometry to find a mathematical formula for the area and what we actually want to optimize. Here it's more already applying known formulas. For instance, the formula for profit, the formula for revenue, right, is P times Q, and so on, right? So if you know all this, you just plug in what is given to you in the text, right, and use it to compute one single formula for profit. And of course, since it's a business application, we want to maximize profit, so pi is eventually the function we want to maximize. Okay? So in this sense, I think this problem is a little bit easier than the previous one. I mean, provided you know the definition of profit and definition of revenue and so on. And once we have this function for the profit, right, this function here, we can do all kinds of things now using calculus, using derivatives. In particular, we can now look at B and C, where we're asked at what production level earns the company the largest profit. So that is just means now find the global maximum, right, of this function. And what is the largest profit possible? That's just the value at the global maximum. Okay, so let's bring this over to a new slide. Here's our function, right, and we want to find the global max. Note again that just as in the previous problem, this is a parabola that opens downward, right? So the global max of this function will be just the top of this parabola. Right, so it will be just to find any local maximum in this case will also be a global maximum. Okay, how do we find the maximum? Well, as usual, we compute the derivative. So in this case, it would be pi prime would be minus 10Q plus 3,996. Okay, so this gives us the critical value, where we have to put this to 0, and this gives us Q equal to 399.6. We can do the second derivative tests again, right, and compute P double prime, which would just be minus 10. So in particular, the function is concave down everywhere, which is not a big surprise given that we already noted it's a parabola, right, face that opens downwards. So it's a concave down function everywhere. So in particular now, by the second derivative test, this is negative, function is concave down. That means this here is actually a local maximum, and since it's a parabola, it's actually a global maximum. Okay, so this is our desired value, production value. So this answers B. Okay, so this is the answer for B. So in B, we were asked to find the production level for which we get maximum profit, right? Production level means how many units do we produce, and that's Q, right? And then in C, we're asked what is the actual profit we make, right? And now all we have to do is plug this Q in to this function, right? And then we get the actual profit. So what we'd have to do is compute minus 5 times 399.6 squared plus 3996 times 399.6 minus 5. And if you plug this into a calculator, you will see that this is about 797,596.80. Okay, so that's our maximum profit that we can obtain. Right? And as I said, this text problem I think is a little bit easier, provided you know the function for the formulas for revenue and profit and so on. Because in the other problem I found that a little bit trickier, because you actually needed to first set up the situation, then think about it geometrically, from the geometry infer the formula, and so on. Whereas here the formulas are more or less given, you just have to plug in everything. Okay. But in general, again, let me point this out, in the first step you just have to extract everything you can get from the actual statement and put it into a rigorous mathematical formula. And that's often the hard thing. That's the very difficult thing for many students, and myself included. I often have problems with these kind of problem type too. So you have to be very careful, parse every word, and think of what does this mean mathematically? How can I express it mathematically? And once you have done this, you're almost done, because then usually the mathematics that you have to apply is not that hard. Okay, so I hope this helped you a little bit with the problems for this week and the quiz preparation for this week.